What's going on, everybody? This is Mr. Diamond here with our example problem for kinetic energy. This is the ones that was in the notes video that should be attached to this. A car is traveling at the following speeds and has a mass of 1,400 kilograms. I reworded it because I wanted to make this as confusing as possible. 20 meters a second, and then what's the kinetic energy at 30 meters per second, and then work done to go from 20 to 30 meters per second. So in this case, we're going to use our equation. Kinetic energy equals 1/2 the mass times the velocity squared. And for these first parts, we're not actually going to need to do a whole lot of thinking. It's actually going to be pretty straightforward. So when it's going at 20 meters per second, KE equals 1/2 times m times v squared. 1/2 times mass is 1,400 times 20 squared. And we'll go ahead and plug that into our handy dandy calculator. 0.5 times 1,400 times 20 squared. We get a very big number. I get 280,000, and then this is kinetic energy. If we look at our unit, we would have meters per meters, and then velocity would be meters over seconds. Or sorry, kilograms, and then meters over second squared. So kilogram, meters squared, second squared, that would be in units of joules, which is the unit of energy and the unit of work. Now, at 30 meters per second, we're going to do the same thing. We get KE equals 1/2 mv squared. We get 1/2. Mass stays the same. You can't change that while you're dealing with the kinetic energy, but we've got 30 squared. If we plug that into our equation, 0.5 times 1,400 times 30 squared, we get 630,000 joules. Now, the other example that I did and I talked about was if you doubled the speed, by what factor would it increase? You would think maybe doubling the speed would double your stopping distance, but it would actually square your stopping distance. Increasing by a factor of 2 means it would go 4 times as much. I wanted to prove that here because this is only half again as much faster, and yet it is more than double the kinetic energy that it has, that it contains, which means, and the reason that it works for stopping it is because this is the energy you'd have to overcome to get the thing to stop. Now the last question though asks how much work to go from 20 to 30. And here we're going to use our handy dandy thing that we mentioned back in the last section, which is the work energy theorem that we gave an actual equation to here, which is the net work, so W net, the net work is equal to the change in kinetic energy. Change in kinetic energy just means the kinetic energy at the final point minus the kinetic energy at the initial point. So at the final point we had 630,000. The final point we had 280,000. So we're going to end up 630,000 minus 280,000. We get 350,000 joules, again because this is in joules, of work. So in order to accelerate 10 meters per second faster, if your car weighs 1,400 kilograms, it's going to take you 350,000 joules of work. Gives you an idea that joules are pretty small here. Now this idea that work equals the net or the change in kinetic energy will get expanded later on when we start talking about potential energy and some other different types of energy. But this will still fundamentally hold true. It just will get a little more complicated down the road. So I hope that makes sense. If you have any questions, this is, like I said, some pretty straightforward calculations here. Let me know. We can work on them in class, or I can answer them through email as best I can. Otherwise, though, this is Mr. Diamond signing off. Have a great rest of your day, everybody.